Good day, everyone. Welcome. We officially are going to be starting Unit 2 today, okay? Understand, Unit 2 is basically all about polynomials. And the basic way to describe a polynomial is it's any type of quadratic, or I shouldn't say that. It's any type of basically constant, which is no x, up until any type of x to an exponent value you can get, okay? So you know these pretty basically as like quadratics, cubics, quartics, if you got four of them. We're going to start discussing how can you figure these out with any type of value in front of it, okay? Now, here's kind of the interesting thing about this unit in general. We'll talk about this in the class. In a typical setting, like within an actual classroom, we would be practicing without a calculator, okay? On top of that, usually the test itself is also without a calculator. Now, this unit, a lot of the math in general that we're going to be doing involves that mindset. Like, if you didn't have a calculator, could you come up with the picture of this graph? Okay. A lot of the things we do comes from that. But here's also the thing with that. With remote learning, since you have a calculator, a lot of these problems should be straightforward for you because at the end of the day, you can always check your work. Okay. So no, a lot of what this section is going to be is graphing, understanding the graph. What do these values and these points tell us? How can I use technology to help me out? And just continuing on that whole idea of we're going to be trying to graph these out without having to use technology, but at the same time using it to our advantage. Okay, using it to a situation where I could say like, okay, can I check my work or something like that? Okay, but before we can do any of this, we truly have to understand the basic idea of very basic polynomials. Okay, so that's kind of the first thing that we're going to discuss, and we're going to do it today using our calculator and using regression. Okay, we've done regressions already. We've done the power regression, we've done linear regression, where if I give you a set of data, we can input that in the calculator and actually come up with a certain value or a chart that can actually be turned into a specific type of equation, as long as we know that only specific data can fit specific types of regression. So in this situation, we're doing a scientific study on sunspots, okay? And in the chart down here, they're basically saying from 1990 up until 2000, the sunspots, which are listed over here on the right, that's how many happened in that year. So what we're going to do is we're going to analyze the years since 1990, which is this column, and actually apply it to how many sunspots we have. So obviously, as you can see, I filled in the chart here. I literally just counted down 1991, that's 1 year past 1990. 1992, that's 2 years past 1990, and so forth, okay? So we're building this data set for us. Now, before I even do anything with regression or anything like that, because maybe some of you are coming up with specific ideas of like, okay, I know what certain regression this is going to be or things like that, let's discuss what's happening. So in your next two questions here, they're basically asking, can it be a linear function or can it be an exponential function? And I want you to try to think about each of those, all right? If I just think of a linear model, I'm usually going to be going in two different types of aspects. I'm either increasing or I'm decreasing, but I have a constant rate of change, okay? Next one would be an exponential model, okay? So if I had an exponential, once again, we want to analyze and why can it or can it be these? Well, in an exponential model, I'm either increasing at a very large extent because the exponent gets bigger. Or I shouldn't say the exponent, because the value gets bigger because of the exponent. As the exponent increases, the number is going to be bigger. Or I get the other model where an exponential starts really big, but then decreases as I go along. That would happen if I had like 5 to the negative x. Okay, as x gets bigger, my answer gets smaller. Okay. So when I analyze these, I want to note that in all four of these graphs, either linear or exponential, I have a clear increase to decrease or decrease to increase. Okay, I shouldn't even say that. We have a clear increase or decrease. Okay. For example, in our linear models, this example is just increasing at a constant rate. This example here is decreasing at a constant rate. Well, if I look at my data, I can already sit here and assume that that's probably not going to happen because up until this point, it's decreasing, but all of a sudden after that 9, it goes into an increase. So I get this number where it's going to start to look like this, which should hopefully bring back ideas of what you think this graph's going to be. I am decreasing at the start of the problem to an all of a sudden an increase at the end of it. Okay? So really for the next 2 questions here, they're just asking like, can they have those models? And we just want to think logically, like, why can't this be linear and exponential? Well, now in our next step, let's just talk about what this is going to be. So in the picture here, I actually drew the graph itself. Okay, that is the actual graph of the function with each of those points plotted. But at the same time, we want to kind of understand like, all right, well, what type of function is this? Well, if you go back to your Algebra 2 days or even probably Algebra 1 days, hopefully remember that any parabola type figure is going to be a quadratic function. Okay, this graph resembles the equation ax squared plus b of x plus c. Okay, in that those values specifically given to me right there is going to create the graph like this. Okay, so let's go ahead and use the calculator to come up with what equation this is going to be. Note when I do this, I'm going to follow the same exact motions that I did in the last unit. I'm just going to plug in a different type of regression. So I'm going to go to stat, I'm going to go to edit, and I'm literally going to look at all my values. Okay, notice how on list 1, I'm 1 through 10. List 2 is the values of each of the sunspots, basically what we had on the other chart. Well, what I'm going to do now is I'm going to go to stat, I'm going to go over to calculate, and I'm going to look for the one that says quad reg. That stands for quadratic regression. So when I hit that, I want all my values, and it's going to tell me my specific equation. Okay, where a equals 6.011. So let's go ahead and write that down. A equals 6.011. B equals negative 67.513. So B equals, oops, is it negative? Let me double check. Yep, negative 67. Ooh, my marker got turned off somehow. Negative 67.513. And my letter C is going to be 204.983. 204.983. Which in turn, I can just turn into the equation 6.11 x squared minus 67.513x plus 204.983. Okay. And just like that, I've created a model regression for this problem. Now, in number 6 and even number 7, they're starting to talk about like what are some important features about the graph. Okay. So once again, let's talk about how we can use technology to help us out. We can actually use this graph, we can actually use technology to kind of guide us in a lot of this problem. So if I go to the graph itself, or excuse me, let me go to y equals. Let's actually plug this in. So we had 6.011 x squared minus 67.513x plus 204.983, right? That was our actual equation. Well, we can actually find some important features from this graph, okay? For example, like the maximum minimum, any type of x-intercepts in this problem, okay? Things like that we can all use to our advantage, especially if we're analyzing data, because who knows when this data is going to be important, okay? So once again, I plug the equation in, and if we hit graph, a lot of us are in our standard form, and it's just not going to fit, okay? Notice how the graph really doesn't fit. Well, it's also because I have to change my window so that these values from this original chart can really fit into it, right? Well, let's think about this. X goes from 1 to 10. So for my X min, let's just go 0 to 10. Okay, that way all those coordinates from this data point is going to be plotted. Next, think about my sunspots here. This is like my Y values. Okay, my lowest value is 9. My highest value is 146. So I want to be able to include all those when I'm changing my window. So let's say for my window, my Y min, let's just go 0 because 9 is my lowest. So let's go a number that's a little bit lower. And for my Y max, let's go ahead and do 150 so that all those values are going to fit in. Now when I hit the graph button, my graph shows as shown. Okay. So that's just me adjusting my window based on the data that's shown here. My X min and max is based off my X's. My Y min and max is based off my Y's. Okay. And so let's talk about where we can find some important pieces of information. So your calculator can do some really nice things here. Okay. And hopefully you are, at this point in time, you are very comfortable doing a lot of these things. But if you're not, once again, listen to this and just kind of understand where we can find specific things. So when I look at this graph, one of the key points here I look at is that this graph has a minimum. Okay. But we can't use this data chart here to figure out a minimum. Okay. We can't assume that 6 is the min, right? We cannot do that. Because the thing we have to understand is that maybe at 5.6 we had a minimum. Okay, maybe at like in between something it gets lower and then has an increase. So we can't use the data chart based off the quadratic regression here because we want to know the actual relative minimum. So in this problem, we can actually find that using our calculator. If we hit second trace, which takes us to the calc button, they basically give us all these different options that we can use to help solve things from this chart. 0 tells me my x-intercepts. Maximum and minimum are pretty straightforward. We've used intersect before where two lines cross. So in this case, let's go ahead and try to find the minimum. Well, your calculator is pretty standard. It always is going to ask this. It's always going to ask a left bound, a right bound, and a guess. And to be honest with you, if you even remotely go on the left and right-hand side of the minimum, you'll be all right with this. So let's just say I can go way over here on the left-hand side, hit enter. And then what I want to do is basically include that minimum within that bracketing. So notice how I put my point left and right because I basically want to try to include that minimum in between those two lines. Now at this point, the calculator just says guess, and being honest with you, I've never even noticed if a guess really matters. I think you just have to be in between those lines. And then we get to our value here. Our minimum is x is 5.6, y is 15.4. Okay. And that's just using the calculator to help us out. Okay. But like I said, there's some important key points. As long as we're able to gather the equation in a regression, now we can use that equation to our advantage. So let's quickly just talk about one more. Okay, let's just say we didn't really care about the years since 1990. Let's say we had this particular chart right here, where we were given the years as well as the sunspots all the way up to 2005. Now, if you notice, we have an actual increase and decrease shift here. Up to this point, we have a decrease. After that, it increases. Then note, once I hit this point, I'm actually going into a decrease again. Okay? Because it goes from 22 to 120 and then starts to go back down. Well, hopefully you're starting to look at that and say, okay, well, how many graphs shape this figure where it decreases to increase back to a decrease? Now, the thing you might be thinking is, okay, well, that looks like a cubic function. And hopefully you did say that and you're absolutely right. This comes out to be a cubic function, okay? How I always look at this is that you have two total turns. You have a minimum and a maximum, okay? Anytime you have two turning points, you always can be able to figure out how many actual values you have, okay? For example, x squared has one turning point because if I took x squared and subtracted 1 from the exponent, that would tell me I only have one turning point. And x cubed, if I want to look at that and say, okay, how many turning points does that have? I just take the exponent minus 1, and it should have 2 total turning points. Okay? Well, in this cubic function, we have 2 turning points, which basically tells me this has to be an x cubed. Okay? Now, instead of going through the time of plugging all those numbers in and basically slowing down this video even more than it already is, basically what we could do, and just to show you it, is if I wanted to figure out the regression of a cubic function, I would follow the same rules. I would go to stat, I'd hit edit, I would plug all my numbers in, and then when I go back to stat, I'd go over to calc, and I'd get a cubic regression. Okay? Now, once again, after doing this quite a while, I'm pretty confident a lot of us can just plug numbers in the calculator. So I won't take the time in the video to actually go through this process. But I do want you to note that basically in any type of equation, we can solve it based on what we see. Okay? One of the key things that we're going to have to get comfortable with is understanding what type of graph do we have. For example, like let's just say I had a quartic graph. Okay? Well, we need to understand that a quartic graph looks like this. Okay? Notice how I have 3 turning points in this figure. Okay? So a lot of this first lesson is A, dealing with regressions, being able to use them, but B, getting the basic idea that we have to understand the graph, what it's giving us, and then use that to be able to determine like what are we dealing with, how we're going to be able to solve this out, and so forth. Okay? But besides that, that's the main part of the lesson. We'll be going over this tomorrow in class, talking about a few things. Besides that, have a great day, and I will see you in class tomorrow.